Welcome to Lecture 2 for Chemistry 141. So first thing that we're going to talk about is some of the looking at some of the values that we had gone through in Lecture 1. And one of the first things we're going to look at is how to handle zeros and significant figures. We haven't used the term significant figures before, but these are the values within a measurement that we know are actually measured or estimated. So your significant values include the certain values that you know of, and then that first uncertain value that you estimated. And when we have zeros contained within a measurement, they pose an interesting problem because we have different ways of handling zeros depending on where they show up in a number. Sometimes those zeros count as significant, and sometimes they do not. And it is very important to understand when they are significant and when they are not. So let's take a look at just some examples here that use zeros, except for this first one, and we'll look at how we count our significant figures differently depending on where zeros are in the values. Now this first one, 5.6, we can see that has two significant values, the 5 and the 6. 10.6, that has three significant figures. So I can write a 3 on there. There we go. And we have 0.6. Well, as it turns out, that only has one significant figure. And then 0.60 has two significant figures. And so there we see two values, or three values with zeros in them. Where sometimes we count the zeros, sometimes we do not. And in that last value, one of the zeros counted as significant and one of them does not. So why do we treat the zeros differently in these different numbers? Well, it depends on where they fall within the number. Anytime we have a leading zero, that's a non-significant number. And a leading zero is a zero that comes to the left of any non-zero number before any non-zero number has counted. So for example, that 0.6, we could write that number as just 0.6, and it doesn't change the value of the number or the accuracy of the measurement. If I'd wanted to, I could just write a series of zeros out in front of that 0.6, and it doesn't change my measurement at all, nor does it change the number of significant values. And so these here are all leading zeros, and so we don't count them as significant. So when you're moving left to right, you don't start counting until you get to a non-zero number. So this zero here in our 0.60 is also non-significant. However, this number here, this zero, is significant because that comes after a non-zero number, and it also comes after a decimal point. And so that is a trailing zero that comes after a number or within a number, such as up here in the 10.6. Those both count as significant digits. So let's just do a real quick concept check here. So we'll look at some values. We have maybe a burette measurement at 20.20 milliliters. So our significant figures there is going to be 4. Both the 2's and both of those zeros are significant. Our uncertainty is going to be in the hundredth of a milliliter, so plus or minus 0.01 milliliters. We have this measurement here, which numerically is exactly the same, but as far as a measurement, it's very different. The zero that's here does not count as significant. That's a leading zero. And so really what we have is this 20.2, and so that has three significant figures. And now the uncertainty is in the tenth of a milliliter, so plus or minus 0.1. We have perhaps a mass measurement with a 4-place balance here. We have two different sets of zeros here. We have two leading zeros. We have this zero here, that's leading, and this one here is also leading. Even though that second zero is after the decimal point, it does not come after a non-zero number, so it just serves as a placeholder between the 2 and the decimal point so that the number has the proper value. And now we can count the significant figures, and this one is going to have 3. The 2 and those 2 zeros are all significant. And its uncertainty is in the tenth of a milligram, or a 10,000th of a gram. Now here's a little bit of a tricky one, $52.85. Well, I might say that that has 4 significant digits. However, it is in fact a counted value, which means that it is an exact number and the number of significant figures does not apply. It has an infinite number of significant figures. It is exactly 52.85, and its uncertainty is not applicable. So a little bit of trick there. It's really important to know when a number is exact and when it is measured. Now, when we're doing math with significant digits, we do have to take into account the accuracy of the measurement and the number of significant figures in that measurement. Now, when we're looking at a final answer, the answer that we report cannot have any non-significant digits. This is a little different from maybe how you did calculations in a math class where you have certain rules to determine how many decimal places get reported. It's very different when we're doing math with measurements. We have to make sure that our final answer has only significant digits in it. So how do we count the number of significant figures we're allowed to have? Well, it depends on what functions we're going to be doing for our math or combinations of functions. Multiplication and division are handled in a similar manner, and addition and subtraction are also handled in a similar manner. But those two groups of functions are handled differently, and we'll take a look to see how we do both of those. Now, if we're doing multiplication and division, the results of these two operations cannot have more significant figures than the lowest number of significant figures for your data points. And so if we have two values, 2.0 times 2 equaling 4, we have a measurement with 2 significant figures and a measurement with 1 significant figure, and that means that our final answer can only have 1 significant figure. So we just can only report that as 4. If both of our measurements have 2 significant figures, then we are allowed to report 2 significant figures in our final answer. So here our answer would be 4.0. And this is one that's a little bit more tricky. We have 2.0 times 8. Again, our lowest number of significant digits is 8, or I'm sorry, just 1 for the value of 8. And so our final answer can have no more than 1 significant digit. Well, when we multiply 2 times 18, we get the value of 16. That has 2 significant figures. We're only allowed to have 1 significant figure, so we're going to round that up to 20. Now, when you report the value of 20, we don't really know if that has 1 significant figure or 2 significant figures, so a better way to report that would be as 2 times 10 to the first in scientific notation. And now we see that this value has only 1 significant figure, and that's what our answer should have. Well, let's look at some calculations that we might do with some multiplication and division. One of the values that we explore is density, and density expresses how much matter is in a stated volume. And so we can write an equation for that where we say density is equal to mass over volume, or just m over v. We see a little m for mass and a large V for volume. You can express density in any mass units or any volume units. In the scientific world, in chemistry, we generally use grams for our mass unit, milliliters for the volume unit, but you will see different units used in different disciplines. Occasionally, even in our class, you will see volume expressed in centimeters cubed. That's the same as a milliliter, so those values would actually be the exact same. Now, one of the neat things with density is it does not change with sample size. So if we wanted to look at the density of something like gold, it doesn't matter if you're looking at a small gold ring or if you were looking at an entire brick of gold, those two samples would have the exact same density. Now, when a property does not change with sample size, we call that an intensive property, which is what density is. Another intensive property would be something like color. Color of gold is the same whether you have a small piece or a large piece. If we have properties that do depend on amount, then we have things that are extensive properties. Examples of those would be mass. If you have a larger sample, it's going to have more mass. Or if you have, or volume is also an extensive property. If you have a larger sample, it's going to take up a larger volume. So one of the more interesting things with density is the fact that you have the ratio of two extensive properties that end up giving you an intensive property. That doesn't always happen. It just happens to occur with density, so it's kind of neat. When we're doing calculations with density, we do some calculations for that every once in a while. We are converting between two different properties, and so what it allows us to do is density allows us to relate volume to mass in a very quantitative manner, and it allows us to convert between any three of those values as long as we know two of them. So as an example, we might want to know what is the volume of 4 grams of gold if its density is 19.3 grams per milliliter. Well, we could just set that up. We know that density is equal to mass over volume, so we could say that we have 19.3 grams per milliliter is equal to 4.00 grams per my volume, which is something I don't know. So we could go through and calculate that if we wanted to. We're not going to right now, but if you want to carry that out, you are certainly welcome to. And here's just an example. It's a picture out of the book I always think is kind of neat. It shows some of the properties of density with different materials. If something is more dense than something else, it will sink below that if it has the ability to here. So here we have two liquids, mercury and water, and in between them we have some copper shot. And so mercury has a density that's greater than copper, if that's copper, and so the copper floats on top of the mercury. Even though it's a solid, it's floating on top of that liquid. However, copper is more dense than water, and so it's actually sinking in the water but floating on the mercury at the same time. So just kind of an interesting picture. Let's get into something that's a little bit more chemical, and that would be energy. We have two primary types of energy that we look at in chemistry class. We have kinetic energy, and this is associated with motion, and we also have potential energy. Now, potential energy a lot of times is associated with position if you're in a physics class. In a chemistry class, we generally look at potential energy in terms of composition. So this would be like a chemical potential energy. We do look extensively at both types of energy, mainly because of the concept of conservation of energy, where energy is converted from one form to another. So we're moving between kinetic and potential, depending on what's going on. But the total amount of energy, either kinetic or potential, remains constant. We do have some energy units that we want to use, and we do want to make sure that we're keeping our units straight whenever we're doing our calculations. We have two very common energy units that we use in chemistry. The SI unit that we use is called the joule, and the non-SI unit that we use quite frequently, even in our everyday lives, are calories. And calorie, again, is non-SI. The size of a calorie and a joule are at least similar. The calorie is larger than a joule. 1 calorie is 4.184 joules. And notice that I've got on here that this is an exact number. So this is not a 4 significant digit number. This is an exact number, which is nice because it means it does not limit our number of significant figures. This has an infinite number of significant figures. Now if we want to take a look at two values here, sometimes you'll see calories reported with a lowercase c, and sometimes you'll see calories reported with an uppercase c, and they are very different. The calorie that's listed first with the lowercase c is the calorie that we have here. It's equal to 4.184 joules. This is actually a kilocalorie, so it's 1,000 of our little calories, and so this is also called a food calorie. And anytime that we look up our calories in our food items, they are actually reporting those larger calories, the kcals. And so it's just always important to keep those straight. In this class, we will always use these calories here with the little c. Now when we're talking about energy, generally what we are most interested in is our change in energy as a reaction takes place. we mentioned that energy can be transformed from one form to another. It can also be moved between objects. And so again, energy is still conserved, but the amount of energy lost by one thing is going to be energy gained by another. And in this way, it's a lot like money. If you buy something, you are losing money out of your pocket, and whoever you're buying something from is gaining money. The money is going into their till. And so energy is very much the same way. If something is losing energy, something else must be gaining it. In any process that loses energy, so a system that loses energy, we refer to that process as being exothermic. And if we're looking at a sign for a change in energy, that sign would be negative because something is losing it. It would just be if you are spending money, you're losing money. And if you were to write that down in an accounting sheet, that would be negative money because it's going away from you. If the process is gaining energy, or if a system is gaining energy, then that process would be endothermic, and the change in energy there is positive. Just like when you get a paycheck, your change in money is positive, and so same thing with energy. So we're going to talk about these changes in energy in a lot more detail much later in the course. We just wanted to introduce these terms because they do get used occasionally early on in the course, but we don't explore them with a lot of detail. But just make sure you understand when something's exothermic or endothermic that energy is either leaving or being absorbed. Now, unit analysis, also called dimensional analysis, is something that we really do stress heavily in this course, mainly because it does give us a way to make sure that a calculation has been done properly and that you get an answer that makes sense in terms of the units. So we do try to illustrate unit analysis every time we do a calculation. Unit analysis also gives us some hint as to how our calculation can be done, even if we don't know the equation that we're supposed to use. A lot of times we can use dimensional analysis to figure out what we need to do. So as an example, we can go back to a density equation here. We want to know how much volume 6 grams of mercury contains, and with knowing the density at 13.6 grams per milliliter. Well, we know that density is equal to mass times volume, but let's say we didn't know that. Let's say we just write down our density value at 13.6 grams, and I'm going to write it per 1 milliliter. Okay, and I also have a value of 6.00 grams. Okay, well, because the grams per milliliter is actually a conversion unit, I can also write that as 1 milliliter per 13.6 grams. That's just like saying that we have a dozen eggs per one dozen, or we have 12 eggs per 1 dozen, or we have 1 dozen eggs per 12 eggs. So we can actually write our density that way, and we can just multiply that, and that will allow our grams to cancel and leave us with just milliliters, and we get like I think it's 0.42. I'm at the edge of my screen there. 0.4 milliliters roughly. Okay, I think it's 0.42. But here we didn't even have an equation set up for volume, mass, and density, but using a unit analysis we were able to figure out how to do that calculation. And so we do have that conversion factor there. Sorry, that's kind of getting in the way. We do have that conversion factor of 13.6 grams per milliliter. So as it turns out, density serves as a conversion factor between mass and volume. Anytime you have something per something else, it can serve as a conversion factor. And when you have a conversion factor, we have 13.6 grams per milliliter. We can invert that and get 1 milliliter per 13.6 grams. Again, very similar to what we do with dozens and 12s. So when we're doing unit analysis, just a general method that you want to use, you want to write down the given value, okay, or any values that you're given. Find a conversion factor so that an original unit that you know is not going to show up gets canceled out properly. And then you can perform that calculation by doing the multiplication, canceling out any of the units that should be canceled out. And then you may need to actually repeat that to get to the final units that you want. And as an example of that, you can do this one on your own, but we'll talk through it a little bit here. Let's say we want to find the number of seconds in 2.2 weeks. Well, we don't have a conversion factor between seconds and weeks. However, we can convert weeks to days because we know that there's 7 days per week. Once we know the number of days, we can convert into hours because we know there's 24 hours in a day. Once we know hours, we can go to minutes. There's 60 minutes in an hour. And once we know minutes, we can go to seconds because there's 60 seconds in a minute. So if we have time in class, we'll look through this one. If we don't get to it in class, try it on your own, and you're always welcome to come on in and show us your work, and we can see if you did it correctly. Well, this finishes out Lecture 2 for Chemistry 141. And as you'll hear on all of these lecture captures coming up in the semester, if you have any questions on anything that was covered today, please make sure you come see your professor.